Dear students, today we will discuss hydraulic turbine Pelton wheel. So let's start. So before going to the Pelton wheel, let's try to understand what is hydraulic turbine. A hydraulic turbine is a prime mover that uses the energy of a flowing water and convert it into a mechanical energy. So classification of a hydraulic turbines. Number 1, according to the head and quantity of water available. Impulse turbine. High head, small quantity of flow. Reaction turbine. Low head, high rate of flow. So under impulse turbine you will find Pelton wheel. Under reaction turbine Francis and Kaplan. Basically this turbine can be classified into 3 categories under this one: low head, medium head, high head. So according to the name of the originator, Pelton wheel, Francis turbine, Kaplan turbine. This one, according to the direction of the flow of water in the runner. Tangential flow turbine, that is Pelton wheel. Radial flow turbine, nowadays these things are no more used. Axial flow turbine, Kaplan turbine. Mixed flow means radial and axial flow turbine, which is Francis turbine. This is the block diagram of a Pelton wheel, where nozzle is connected in the penstock where the water is coming out, and it will strike the bucket of the Pelton wheel. After striking, it will rotate, and due to the rotation of the bucket you will get the EMF is produced in the generator. So finally you will get the electricity. So this is the simple diagram how Pelton wheel work. So this is the typical velocity diagram of a Pelton wheel. This is your bucket. This is the blade or vanes of the Pelton wheel, where water is basically coming out from the nozzle, strike in the center, and the water will come out in this direction. So inlet velocity diagram, V1, this is V1 absolute velocity, U1 circumferential velocity, VR1, this is the relative velocity. Similarly for the outlet velocity triangle, this is F1, this is F12, which is the flow velocity, V2 absolute velocity, VR1 relative velocity, this is circumferential velocity, this is the velocity of wheel. This is the angle of deflection here. This angle is called beta, this angle is called phi. So regarding the nomenclature of the all those things, those are the nomenclature. Okay, and speed of the wheel in RPM, d diameter of the wheel, small d diameter of the Z, U is circumferential velocity of the runner, which is equal to U is equal to U1 is equal to U2, that is circumferential velocity of the runner at inlet and outlet is same. V1 absolute velocity of water at inlet, VR1 Z velocity relative to the vane or bucket at the inlet, alpha angle made by the direction of the Z, and direction motion of the vane, which is called guide angle at inlet, theta angle made by the relative velocity VR with the direction motion of the inlet, it is called vane angle at the outlet. So here theta is also 0 and alpha is also This both are 0 for inlet diagram. Vw1 the velocity of wheel at inlet and Vf1 velocity of flow at inlet. V2, Vr2, Vw2, Vf2 are the corresponding value at outlet. So phi is the angle made by the relative velocity Vr with the direction motion of the vane. So this is called vane angle at outlet. This one. And beta angle made by the velocity V2 with the direction motion of the vane at outlet. So this is your beta. So here these both are 0. So here this is so depending upon the beta, suppose it is less than 90, it's called slow runner, and Vw2 is negative. Medium runner, beta is equal to 90, Vw2 is 0. This one is called radial. And fast runner, beta is greater than 90 degree, where Vw2 is positive. So depending upon the situation, your outlet velocity triangle may vary. So those are the three possibilities. Now let's consider, this is suppose our velocity diagram for this derivation, outlet velocity triangle or outlet velocity diagram. The force exerted by the jet of water in the direction of the motion is given by F rho A V1 Vw1 plus Uw2, where rho is the density, A is the area of the jet. Now work done by the jet on the runner per second will be F into U. So F is already derived, this is given by this into U. And work done per second per unit weight of water, is given by rho A V1 Uw1 plus Uw2 into U divided by weight of the water. So weight of the water is given by this. So ultimately, after simplification, you will get 1 by Z V1 W1 plus Vw2 into U. Now the energy supplied to the jet at the inlet is in a form of kinetic energy, and which is equal to half of mv1 square. And kinetic energy of the jet per second is given by half of rho A V1 into V1 square. So mass per second is given by rho A V1. So the hydraulic efficiency of a Pelton wheel, this is work done per second divided by kinetic energy of the jet per second. So work done per second is given by rho A V1 Vw1 plus Vw2 into U divided by kinetic energy per second is half of rho A V1 into V1 square. So after simplification, you will get 2 into Vw1 plus Vw2 U divided by V1 square. Now from inlet and outlet velocity triangle, we have, this is inlet and outlet velocity diagram. So VW1 is equal to V1 and VR1 is equal to V1 minus U, and VW2 is equal to VR2 cos phi minus U, and it can be replaced by KVR1 because VR2 is equal to KVR1, and VR1 is equal to U minus V1 minus U. So if I put here this value, so here we are getting VW1 is V1 and VW2 is equal to this. Now you have to put these two value in the hydraulic efficiency of this one, and you will get this is the value, and after simplification you will get 2 V minus U bracket close 1 plus K cos phi whole into U divided by V1 square. So this is the hydraulic efficiency of a Pelton wheel. Now let's find out the maximum efficiency of a Pelton wheel. For that purpose we are considering that maximum efficiency can be achieved for the value of V1. Suppose V1 will be remain same. If V1 will be remain same, then whole efficiency can be differentiate with respect to U. The hydraulic efficiency is equal to 0, give you the condition. So let's differentiate this whole hydraulic efficiency is equal to 0. After simplification you will get 2 plus 2 into 1 plus K cos phi V1 square is a constant. This remain constant, so it cannot be 0. So in this sense U V1 U plus U square, after simplification you are getting this, because this will be this U will interact this U and this. So after differentiation you are getting V1 is V1 minus 2U is equal to 0. So U1 is equal to V1 minus 2. So hydraulic efficiency of a Pelton wheel is maximum when velocity of the wheel is a half the velocity of the jet of the water at the inlet. The velocity of the wheel is half the velocity of the jet of the water at inlet. Now if you put the value U is equal to V by 2 in the efficiency, you will get the maximum efficiency. So this is your efficiency. Now I am putting the value of, instead of U I am putting V2 by 2, here also V2 by 2. After simplification I am getting 1 plus K cos phi by 2. So where is a blade friction factor actually? If blade friction factor is K is equal to 1, then your maximum efficiency will be 1 plus cos phi by 2. So your maximum efficiency does not depend upon any velocity. It depends upon the vane angle. So your maximum efficiency depends upon the vane angle at the outlet. This is very important. So let's talk about mechanical efficiency. So mechanical efficiency is a ratio of power available at the turbine shaft by power developed by the turbine runner. So this is basically called shaft power by bucket power. So shaft power is denoted by suppose P, and the bucket power will be rho G QA HR. So what is HR? HR is called runner head. So this is basically 1 by G VW1 plus VW2. This is called runner head, and QA is actual flow rate, actual discharge. Now volumetric efficiency. So volumetric efficiency is a ratio of volume of water actually striking the runner by total water supplied by the jet to the turbine. Overall efficiency. So power available at the turbine shaft by power available from the water jet. So this is P by rho G Q H. So here H is net head, Q is total discharge in meter cube per second supplied by the jet. So this is the actual discharge. This is not actual discharge, this is a theoretical discharge which is actually coming out from the nozzle. And overall efficiency can be derived from all the, if you multiplied all the efficiencies like hydraulic efficiency, mechanical efficiency and volumetric efficiency. If you multiply all the efficiency, you will get the overall efficiency. Here the another most important things, this is the velocity of jet, which is V1, which is coming out from the nozzle, can be derived from this equation CV root over 2gh. So CV is coefficient of velocity and h is the net head. CV, the range of the CV 0.98 to 0.99. Sometimes you can take 1 also if it is not given. And velocity of the wheel, this is the circumferential velocity of the wheel, which is given by KU 2gh root over 2gh, where h is same, net velocity, and KU is called speed ratio. Q is called speed ratio, and their range is also given. Their range is basically from 0.432 to 0.48. Sometimes you can take 0.5 also depending upon the situation. So those are the parameters under which one can identify the characteristic of a Pelton wheel. I hope you understand. In the next class, we try to solve few problems based on Pelton wheel. Thank you. Stay safe.